Hello and welcome to another one of D's ADD videos. Today we're going to be looking at SN1 reactions. This is basically a unimolecular substitution reaction in which the leaving group leaves and it gets replaced by the solvent. Okay, so in this case what we're going to do is look over the steps and then apply it to this wonderful halogenated alkane. We have the first step is the formation of the carbocation, so that's crucial, and if you remember, the stability of this thing was the third or tertiary was most stable, secondary, primary. This is all due to the inductive effect again, and then nothing. Possible arrangements: you can either have a hydride shift or a methyl shift. Those tildes indicate a shift, and they're going to do that in order to increase your carbocation to go from a 2 to a 3 or a tertiary. Alright? Then after that, then the nucleophile attacks. So let's look at this wonderful compound here. We have 1, 2, 3, 4, 5. So 2 bromopentane. I'm going to go ahead and rewrite this so it's a little bit more friendly to what our purposes are. I don't really need to draw anything but the adjacent hydrogens. So this is what we got going on. Again, the first step was the ionization of this bond right here, and what's going to happen is the bromine leaves. Make sure you know what makes a good leaving group. If you don't, watch that video and those examples. But upon leaving, what happens is you get the same compound. You know what? I never gave you the solvent, so I apologize for that. The solvent in this case, well, let's just go ahead and make it methanol. Because it has an H on it, we know it's weak, and that's what tells you it's going to be a 1 reaction. Okay. Then the leaving group leaves to give you Okay, so here what we're going to have is a secondary carbocation because it's attached to 2 different carbons. This carbon is, which is pretty stable. And shifting this hydrogen over there would create a primary carbocation, which is not stable. And shifting this hydrogen over here would create a secondary, which is no more stable than what we have already. So there are no shifts in this case. And what's going to happen is your methanol is going to come in and fuse to this MTP orbital. Okay? And you're going to end up eventually with an ether. So let's see in action. What's going to happen is you'll get CH3, CH2, then you're going to have that bonding to that carbon right there to give you OH, CH3. So what ends up happening here is we end up with a 1, 2, 3, 4, 5 valence electrons around this oxygen, and when it wants 6 of them. So if you wanted to do the formal charge, be formal about it. Yeah, that was bad, sorry. Minus sorry, just got a text, a little distraction there. 3 bonds plus 2 lone pair electrons, which gives me a +1 charge. So there's going to be a plus charge on this. And then that's not a stable compound because oxygen likes negative charges. It's electronegative. So what we end up having to do is the alcohol then comes and picks up this extra hydrogen right here, and you end up with these 2 final products. The ether because it's carbon chain, oxygen, and then another carbon chain. And then we also have the alcohol that's got 2 hydrogens bonded to that oxygen, so it's got a plus charge on it. Okay? And that's the basics of SN1. So recap, form your carbocation. How did we know it was an SN1? Because of the solvent being, oh, that's too big, being methanol there, and the alcohol will guarantee one reaction. Why was it not an E1 reaction? Well, in actuality, for laboratory purposes, these are bad synthesis reactions because you can't dictate whether it's going to be E1 or SN1. It's pretty much what the solvent attacks first. You can use heat to push it further towards E1, but most of the times you'll get both E1 and SN1 products. Okay, so leaving group leaves forms the carbocation. That's a plus charge underneath all that, and then after that we end up with hydrohydromethyl shifts if necessary to increase stability of your carbocation. In this case, there weren't any. And then the solvent comes and it fuses to the carbon, then it has the plus charge on it, and then the alcohol removes this hydrogen because it's causing this positive charge there on my oxygen. Alright, I hope this has cleared things up a little bit. Make sure you check out the example that has a hydride shift as well as the example that has a methyl shift on it. And of course, practice, practice, practice. Thank you and have a nice day.